And welcome again to It'll Be All Right on the Night, gateway to cock-up country. Now, before we go any further, those of you who've questioned my use of that word during peak viewing hours, you might like to know the dictionary also defines cock-up as a freshwater fish found in the estuaries of Indian rivers, a printer's term for the small capital letters sometimes used for the first word of a book, and public school slang for a beating by a monitor or prefect. Now, you can either spend the next 2 or 3 minutes brooding about that, or you can take a look at our first assortment of Indian freshwater fish. These all reinforce that remark the unhappy Mr. Craig Smith made in our opening clip, "Tain't my day," because it presents a group of people whose day was even more tainted.
Well, hello and good morning, everybody. Today we're going to be having a look at this Kirkisui. Morning, everybody. Today we're going to be having a look at this Kirkisui DLG 750 logic analyzer. Now, it's fair to say that I don't actually know very much about logic analyzers. Ah well, what's new there? But I thought it would be useful to have a look at it because well, hello and good morning, everybody. I thought today we'd take a quick look at this logic analyzer, which is made by Kirkisui. And for those playing along at home, it's a DLG 7050. Now, it's fair to say that I don't actually know very much about logic analyzers. Well, nothing new there, is there? Now, it's fair to say that I'm certainly no expert on logic analyzers, and to be fair, I've never even used one before. Well, hello and good morning, everybody. Well, hello and good morning, everybody. Well, hello and good morning, everybody. Now, today I thought we'd take a look at this Kirkisui logic analyzer. Well, hello and good morning, everybody. Well, hello. Well, hello and good morning, everybody. Now, it's been quite a long time since we've had a look at any test gear, so I thought we could do that again today. So what I've got on the bench is this Kirkisui DLG 7050 logic analyzer. Now, I bought this logic analyzer a few months ago from a radio rally, and I have to admit, I think I got it as a bit of a bargain in that I paid the grand total of £20 for this, and I was quite pleased with that, because when it comes to tech porn, you know, you really can't beat having all these pushy buttons and stuff like that. That you know, apart from a spectrum analyzer, one of these will look, you know, really quite good on the bench. So yeah, if you want some tech porn, dig out, go and find yourself a logic analyzer, and if you can score one for £20 like I did here, you're a winner. Well done. Right, now anybody who's watched any of my previous videos won't be surprised to know that I know almost nothing about logic analyzers. I've only ever used one once before, and I thought we could try this one today. So we're not going to take it apart, we're going to plug it in, but we're not going to read the manual because that'd be cheating. Before we dive right in and start looking at this logic analyzer, I think what we'll do is we'll just give an example of why you might want to use a logic analyzer and what its advantages are over some other pieces of test equipment we could use. Is that all right? Now, I'm sure that you'll all remember that a few weeks ago we were playing with this Wi-Fi alarm system, and one of the things that we talked about was this liquid crystal display and how it uses this Attache interface to actually control it and put the text on the screen. So I thought it might be interesting to try and do a little bit of a reverse engineer on this, and you know, have a look in more detail at some of the signals that actually go to make the LCD display the information that it displays. But I think before we do that, we can get rid of you, because yeah, it all got a bit noisy last time, didn't it? So I'm not making that mistake again. This buzzer's going. Is that on? Yeah, it is. He said burning his nose. Yeah, your history. I don't want us to become too bogged down in how this LCD actually operates. The whole purpose of using this alarm board is just to actually generate some simulated digital signals that we can go away and have a look at. But we will just very quickly just have a look at what these digital control lines are that we're going to be looking at. So first pin here is the ground pin, so that's our pin 1. Pin 2 is VCC, which for this LCD is 5 volts. Pin 3 is the display contrast. Now it's quite handy to know what this pin is, this pin 3, because if you ever need to identify maybe the pinouts of an LCD, you will find that all the inputs have standard kind of TTL voltage levels on them, 0 or 5, but you will typically find like 0.7 volts on the contrast display. So there's a bit of a tip there for if you're just trying to find out what pin does what. So you can, that's how I know that on this particular header, pin 3 does happen to tie up with this data sheet, because this is just a random data sheet. But the thing about these LCD character displays is most of them do have the same pinout. It's usually just things like the backlight controls that may change. Anyway, forgot where we got to. So pin 3 we said was the contrast control. Then we've got pin 4, which is a register select RS, and what that's to do is when you actually send a command to the LC display, there's a few different registers in here, and you have to just set this register select pit to make sure that the data you send goes into the correct register. So that's pin 4. 1, 2, 3, 4. Pin 5 is the read write, so that determines whether we're writing data to the display or we're going to be doing a read from it. Pin 6 is an enable, which basically the way I think that this works is whenever you want to strobe data into the display to make it read something, you set the data up and then you actually hit the enable line, and the display then reads in the digital data it's being presented with. And then after that we've actually got the data that we're going to be sending to the LCD. Well, I say data, there's two types of information you'll typically send to an LCD. One of the, and the way you send information, we've got basically 8 bits, so we've got 0, 1, 2, 3, 4, 5, 6, 7, 8. And I'm not explaining this very well, am I? So depending on what 8-bit strings you send to this display, you could either be sending data, which would be a character like the letter A or B or the number 1, or you could actually be sending a control command. So basically these 8 bits worth of data, these 8 pins here, will be either used to send a data, an alphanumeric character to the display, or they will send a control word to the display, and that control word will do things like move the cursor to the middle of the screen, or move the cursor to the home position, or start the cursor blinking on and off. So yeah, so we send commands and data. So we've just got our flute voltmeter set up here. So let's get pin 1, we said that is ground, so pin 2 is VCC, so we should have about 5 volts on there. That didn't work, did it? Why haven't we got any voltage on there? Dodgy connections. Yeah, we'll edit that out. Actually, why aren't I getting 5 volts? Oh, right, okay. I think my probes might be getting a bit rubbish. They feel sharp. I think I'm due for some new test leads, to be honest. Come on, let's try it again. This time I'm sure it'll work. Okay, there we go. So pin 1 is ground, pin 2 is 5 volts, pin 3 is going to be this contrast control, which I'm predicting is going to be about 0.7 volts. Okay, I'll take that, 0.736. Then we're going to have the register select, which is 0 at the moment, 0 volts. So that means that The LCD would at the moment be expecting a command to be sent to it, a control command rather than a piece of data. Let's have a look at the pin 5, which is a read-write instruction. Okay, so that is low at the moment. So in that condition, the LCD would be expected to write some data out from the LCD back to the micro. And the reason you might want to write data out is you might want to find what status the LCD is in, whether it's reset or maybe just read back the contents of the memory. If you've forgotten what you've written to it, you could actually read the contents from the control registers back into your micro. Pin 6 is the enable line. 1, 2, 3, 4, 5, 6. That's got 0 volts on it at the moment, so the display isn't being enabled. And now we're onto these data lines. So pin 7 is data bit 0, and then we've got 0, 1, 2. Oh, we've got some data on pin 2, it's high at the moment. 3, that's high. 4, low. 5, 6, and 7. So now I think we're really going to start to get more into the meat and drink of this. So we've got our LCD display, we're going to be presenting it with data. Now I'm going to set a scene now that we've got our system here that we've designed or we're trying to repair, and it isn't working properly for some reason. Let's imagine we're just getting garbage sent to the LCD display. So what we would like to be able to do is we would like to be able to probe these data and control lines and actually find out what's happening. Now one thing we could do is we could just go in between 0 and let's just choose this enable line, pin 6. 1, 2, 3, 4, 5, 6. We can put our voltmeter on there, pin 6, and we can actually just try making the LCD do something. And we can see that basically there's nothing happening on the voltmeter. There's no change in the display. But we know that the display is working here because the contents on it was changing, but the voltmeter wasn't very good at showing us what was happening. It could maybe show us if there was the line was stuck at 0 volts or it was stuck at 5 volts. That might be useful to know. But I guess what I'm trying to say long-windedly is these data lines here, they're toggling up and down, and there's no way that a voltmeter can actually show that because it's just not fast enough. That enable pin is just rising and falling too quickly to display it on a digital meter. So we'll get that out of the way. Well, I've just been rummaging through the not often used drawer, and I've just pulled out this logic probe, which is the LP2800. Now I'm sure you'll remember this from a previous video that we made where we talked about logic probes. So I'm not going to go back all over that again. Basically, if you want to know what a logic probe is and why we use it, have a look at the past video. But, oh God, wire's going to keep falling off. That was falling off last time, wasn't it? It drives me mad, this. The wires, it's a really old piece of equipment, this, and of course the plastic on it, the PVC, has just gone hard with age, which means that as you move this thing around, it has a habit of pulling the clips off. We'll just do a little bit of probing again, and I'm hopefully you'll be able to see this. Let's just see. So I'm just going to touch the ground pin at the moment. He said if I can get the tip in. Okay. Is that showing up on camera? I think maybe it is. So yeah, you can see that. Okay. So I'm just on the pin one, which is ground. So you can see we've got a green light on, so we've got a low. So if we go to VCC, we're going to get a red light because that would be classed as a high. Okay. And now we've got our contrast control, which it'll be interesting to see what that comes up as. Okay, so our contrast control isn't lighting up at all now. We're not getting a high or we're not getting a low light, and that's because at 0.7 of a volt it's in this indeterminate region, so we're not having to make a decision there, is it high or low. That's clearly not a digital signal because neither the high or the low lamp is lit up on the little logic probe here. So that's kind of handy. Now if we were probing one of the digital pins there and neither of these lights came on, that would indicate an indeterminate state, and you would maybe think, well, there's something wrong with that. That pin isn't high and it isn't low, it's in no man's land. So you might go and investigate that. So now we will go on to pin 4, which is the register select line, and that's low at the moment. Pin 5, which is the read-write control, and that is low. But we can see something happening here. We've got a pulse light on the logic probe, which basically means that that line is being toggled up and down. Now, when we had the voltmeter out, we had a look at the enable line, and I've actually just put this piece of green wire on the enable line, so we'll just have a look at that now. Oh, and I should say that a bit of a trap for young players here. If you're ever wiring up an enable line on a digital circuit, you must use green wire. It's only green wire works. Don't use any other colour, it must be green. Right, okay, so we can see that again this enable line is now pulsing, and it's probably pulsing every time the display is selected. The microprocessor is probably scanning through all the devices it has to talk to on this board, and every now and again it's set up to send write a piece of information to the LCD. So we can see that this is pulsing. Now that is important because when we actually had the digital voltmeter on there, well, we'll put it back on, we'll have another look. I think that was indicating a low. So I'm hoping you can see that. We've now got the digital voltmeter on that enable line, and that just looks like a low. We can't tell whether or not that line is pulsing or not, but it actually is. I hate it. Anybody see that meter? Whenever I'm doing any filming with this fluke meter, you can absolutely guarantee as soon as I switch the camera on, the display on the meter will switch off. So we'll go back. The result from using a voltmeter was indeterminate, but we put the logic probe on, and we can see that that line, that enable line, is being pulsed. Right, I've just moved the camera around a little bit there, so I'm hoping you can actually now maybe see what I'm doing a little bit better. So we're on the first of our data lines here, which is DB0, which is the least significant bit. And again, I think we thought when we were using the voltmeter that line was just held low, but we can actually see that we're using the logic probe that it's not low, it's actually pulsing. So let's just have a look at some of the other data bits. Right, we can actually see that this one is also quite obviously swapping from high to low. I'll just go back to the other one. The reason we're just getting the green and the amber light on there is because it's pulsing too quickly to show it swapping. Well, what have I done? Oh, right, okay. I think I actually pressed a button there accidentally. So now the LCD is showing what you might call a static display. There's nothing flashing on it. So the data on the LCD isn't being updated. I wonder if we can make it flash again. Okay, so now it's got a flashing cursor here. So I suspect what's actually happening is the microprocessor is actually sending data to the LCD to actually switch the cursor on and off. So that's why the data bus has now become alive, whereas before it was just kind of static because there was no update on the display. Okay, and it's now showing a static display again, because again I've just accidentally pushed a button there. And it's interesting that when I pushed the button I was probably shorting out a couple of the data pins. So I've actually managed to put garbage on the display. It looks like it says CL clock SO or God knows. So basically I managed to short out a couple of the data lines there, which has sent some corrupt data to the LCD. But I'm sure if I just press another button it will send, it will refresh the display again and send some new information. So let's just press a button. Okay, so it's come back. Okay, we're not going to look at all them, but I think that's quite an interesting little find we've got there using the logic probe. That if the actual display is doing something active, like flashing the cursor on and off, we can see that the data on the display is constantly changing. It's pulsing. But if we just make the the display go to a static image, which I don't know how we'll do that. Let's just try pressing return. Right, that's a static image now. There's nothing changing on it. And the wire's fallen off. Get back on. Go back to that pin. And of course, because the display doesn't need to be updated because there's no flashing cursor, the data is static. Let's see if we can start it flashing again. Okay, we've got a flashing cursor, and again, so all I'm really saying there is we're getting activity on the data bus. But if I was actually trying to figure out what information was going to be sent to that display, it would be very hard to do. If the data rate was really, really slow, then perhaps we could have, I don't know, perhaps we could have, here's another logic probe, perhaps we could have 2 logic probes. Maybe if we had a really big hand, we could actually set up 8 logic probes and have them all stuck on here. And then as the data changed, we could try and look at the lights and we could try and write it down on a piece of paper. But it wouldn't be practical. So although the logic probe is good, that it actually shows us the highs and lows very clearly, and it will show us when there's something pulsing, which the DVM, which the digital voltmeter couldn't do. The limitation is that it's only really any good for static analysis. If you want to, or rather, it doesn't have any kind of recording function. It really doesn't have much of a memory, and you can only actually look at 1 bit at a time. Now, if you're trying to work out why, for example, you've got corruption on the display, as we have now, because I've been shorting out some of the data lines, you probably find that quite hard to figure out using a logic probe, because it's static. It won't really look at dynamic signals very well, and it certainly won't allow you to look at all of them at the same time. So yeah, so basically we're lacking memory, aren't we? There's no memory function in here. Now we've moved on a step here now, and I think this is actually coming a little bit close to cheating. We're actually straying into the area of what logic analysers actually do. And I can hear you all shouting in the background, get on with it, because in my usual way, I'm just taking far too long to get to the point. But I just wanted to set the stage of why you might want to use a logic analyser over other equipment. And there was another piece of useless waffle. So we've moved on a step. We've connected our oscilloscope probes now to the data lines. And there's an important thing to just note here. We've actually got 8 data lines on this display, but I'm using what I would call, well, it's a high-end oscilloscope, and the oscilloscope I'm using has got 4 input channels. Now, most of us well, not most of us, probably all of us in the 1970s, 80s and 90s, we didn't commonly have these 4 channel scopes. So you got to remember that when we go on to talk about logic analysers. So let's just have a look at. So we've got these four probes hooked up to the data lines. Let's just bring you in on the oscilloscope screen. So we're using all 4 channels of the oscilloscope. Yellow trace here is data bit 0, data bit 1, data bit 2, data bit 3. So that's the first 4 bits of the data bus on the LCD. Yeah, as I say, we're definitely getting into cheating technology here. We've got the oscilloscope set up to, I guess, really replicate what an analog scope would do, in that it's got a fairly fast sweep. Because you couldn't really set a very, very slow sweep and on a cathode ray oscilloscope. Although you could set a slow sweep, you couldn't see anything because the persistence of the screen wouldn't be good enough. But we can see that all the data bits here seem to be relatively static, although bit 1 is toggling up and down. But that's not really painting the whole picture of it. Now, this is where, again, we're starting to go into logic analyzer territory now. I can actually do something on here that you couldn't do on your analog scope, which is probably what the fairer comparison would have been. I'm just going to turn the sweep right down. So you can see now, just by turning the sweep down on the scope to this very slow sweep, we're actually revealing data now. Now the data being sent to the display hasn't changed at all. It's just that when we were using such a fast sweep, the scope wasn't seeing it. Again, we're going to go even further now into logic analyzer territory, and we're going to stop the sweep. And what we'll do is we'll just line this up. On, for example, that point there. So this would have been one of the data bus transactions. So we just zoomed in on there, and now we've got a low, a high. I think that's a high and a low. Let's just zoom out a bit. Oh, we've got a little rump pulse there as well. Let's just find another piece of data that was sent. Just move that along. Let's zoom in there. So now we've got a low, we had a transition to high, that stayed high, and that went low. So I think what I'm basically again trying to explain in my very crude and poor way is we're seeing history here. We can actually trace back in time and actually see what happened on this data bus. And as I say, that's very much getting into where logic analyzer territory is. So I'm going to call it a day at that. I could also have said that a lot of these modern oscilloscopes do have logic analyzer functionality built into them. This is kind of a crude way of doing it if it's all you've got. But you can see there's a dedicated slot here, and you can actually turn this oscilloscope into a dedicated digital logic analyzer, which also allows you to do some analog channel monitoring as well. But that's an add-on option, and I don't do enough digital work to really justify the high cost of that. Well, I think it's actually about time I started talking about logic analyzers, because we've been going for over 20 minutes, I think, and I haven't even introduced the star of the show.